Hey everyone. Ready to get kind of theoretical today?
I'm ready.
Awesome. So, we're going to deep dive into string theory,
Okay.
which, if you've heard of it, it's this idea that like everything in the universe is made of these like teeny tiny little vibrating strings.
Right.
And it was this like huge deal in physics for a while because it was going to explain everything.
It really was. It was incredibly seductive. This idea that we could finally have a theory that explained both quantum mechanics, the world of the very small, and general relativity, the world of gravity.
Yeah, it's like, oh my gosh, those two don't play nice together. And
Yeah,
this was like the missing link.
exactly.
But as we're going to see, it kind of ran into some issues.
It did. Yeah, there were some big challenges.
But let's start at the beginning.
Okay.
Why was string theory so exciting in the first place?
Well, like I said, it promised to unify these two fundamental theories of physics. Quantum mechanics, which governs the behavior of particles at the subatomic level, and general relativity, which describes gravity and the large-scale structure of the universe.
Okay, and those two, like we said, they don't really mesh.
They really don't. They make very different predictions, and physicists have been trying to reconcile them for decades.
And so how did string theory propose to solve this?
Well, the basic idea is that everything in the universe is made up of these tiny, one-dimensional objects called strings. And just like a guitar string can vibrate at different frequencies to produce different notes.
Oh, I like that.
Yeah, these strings can vibrate at different frequencies to produce different particles and forces.
Oh, okay. So like an electron would be one kind of vibration.
Exactly. And a quark would be another. And gravity. That would be caused by the vibrations of a specific type of string called a graviton.
So it's like everything is music.
In a way, yeah. It's a beautiful, elegant picture of the universe.
I love it. Okay, so we had this really promising theory.
We did.
And then what happened? Why do we say string theory is facing a crisis?
Well, one of the biggest issues is something called the landscape problem. String theory, you see, it doesn't just give us one solution for our universe. It gives us a vast number of possible solutions.
Okay.
And each of these solutions, we call them vacuum states, represents a different way the universe could be configured at a fundamental level.
So like a different set of physical laws.
Exactly. Different values for the fundamental constants of nature, different types of particles, different forces.
Whoa, okay.
And we're not talking about a few different possibilities here. We're talking about something like 10 to the power of 500 different vacuum states.
10 to the power of 500. That's a lot of universes.
It's a mind-bogglingly huge number. And this is what we call the landscape, this vast space of all possible universes allowed by string theory.
Okay, so this sounds kind of cool, actually.
Right. But here's the problem. With so many possibilities, how do we know which vacuum state describes our universe?
Yeah, that's a good question. It's like having a map with, I don't even know, a gazillion different destinations, but no starting point.
Exactly.
Yeah.
And this makes it really hard to make testable predictions. If string theory allows for almost any kind of universe, how can we use it to make specific predictions about our own universe?
It's like, if it can explain everything, does it really explain anything?
That's a question a lot of physicists are grappling with.
I see. So that's the landscape problem.
What are the big ones? Yeah.
So where do we go from there? What other challenges does string theory face?
Well, there's another concept that's been generating a lot of buzz, something called the holographic principle.
Oh, yeah. I've heard of that. It's something about the universe being like a hologram, right?
And it's connected to string theory in a pretty interesting way.
Okay, tell me more. This is where my brain starts to melt a little. All right, imagine you have a hologram.
Like on a credit card or something. Yeah. It's a two-dimensional image, right? But when you shine light on it, it creates a three-dimensional image. It's like all the information about that three-dimensional object is encoded on that two-dimensional surface.
Oh, okay.
And the holographic principle suggests that our universe might work in a similar way. It suggests that all the information about our three-dimensional reality could actually be encoded on a distant two-dimensional surface.
So, like, our universe is a giant hologram.
Exactly. It's a pretty mind-bending idea, isn't it?
Yeah, that's a lot to process.
And here's where it gets even more complicated. The holographic principle works really well in a hypothetical type of space called anti-de Sitter space. But our universe seems to be expanding in a way that's more like de Sitter space. And in de Sitter space, the holographic principle doesn't apply as neatly.
Oh, so it's like we have this key that doesn't quite fit the lock.
That's a good way to put it. It's a challenge that string theorists are still trying to figure out.
Okay, so we've got the landscape problem, we've got the holographic principle not quite working in our universe.
Right.
Are there any bright spots? Like, has string theory actually helped us understand anything?
Oh, absolutely. In fact, one of the areas where string theory has been remarkably successful is in our understanding of black holes.
Oh, really? Tell me more.
Yeah, it's helped us to address a long-standing puzzle known as the black hole information paradox,
Okay.
which, it's this conflict between classical physics and quantum mechanics.
Remind me, what's the paradox again?
Well, classical physics says that anything that falls into a black hole is lost forever.
Right. Gone.
But quantum mechanics says that information can never be truly destroyed. So there was this big question, what happens to the information when something falls into a black hole?
Where does it go?
Right. Does it get destroyed, violating the laws of quantum mechanics? Or does it somehow escape, which would challenge our understanding of black holes?
Oh, yeah.
And what string theory showed, which was pretty groundbreaking, is that black holes likely don't destroy information after all. It provided a mechanism for that information to be preserved,
Wow.
which was a huge step forward in our understanding of these really mysterious objects.
So string theory helped solve this paradox.
Yeah, it offered a way to reconcile these seemingly contradictory ideas about black holes.
That's pretty impressive.
It really is.
So even with all these challenges, string theory has given us some valuable insights.
Absolutely.
And one of the most mind-boggling implications of string theory is the idea of the multiverse.
Right. It's that concept that there might be many, many other universes out there, each with its own set of physical laws and properties.
So like a universe where gravity works differently or time runs backward?
Exactly. It's a very speculative idea, but it emerges naturally from some interpretations of string theory. You see, if we go back to that vast landscape of possible vacuum states.
Oh, right, the 10 to the 500 different universes.
Yeah. Well, some physicists believe that each of those vacuum states could represent an actual physical universe.
Whoa. So there could be countless versions of ourselves out there, living out every possible variation of our lives.
It's a mind-blowing concept, isn't it? And it raises all sorts of philosophical questions about the nature of reality, free will, and even the meaning of our own existence.
Okay, I need a minute to process all of that. This is heavy stuff. But before we completely lose ourselves in the multiverse, I want to talk about another aspect of this string theory story that I find fascinating, and that's the human side of it. I mean, we've been talking about these abstract concepts, but there are real people, real scientists who are grappling with these ideas, right?
Oh, absolutely. And there's a really interesting debate happening right now within the physics community about the future of string theory and its impact on young physicists.
Yeah, I've heard about that. There's some concern that young physicists are feeling pressured to stick with string theory, even if they have doubts.
Right. Leonard Susskind, one of the pioneers of string theory, has even spoken out about this, saying that he worries about the pressure on young physicists to conform, to follow the established path, even if they see limitations in the theory or have other ideas they want to explore.
It's like if everyone is focused on one particular path, we might miss out on other equally promising avenues of exploration.
Right. Exactly. And Susskind has been a vocal advocate for more diversity of thought and approaches in physics. He believes that young physicists should feel free to question the status quo, to explore alternative theories, to be creative and take risks.
That makes a lot of sense. I mean, science is all about questioning, exploring, and pushing the boundaries of knowledge, right?
Exactly. And sometimes the most groundbreaking discoveries come from those who dare to challenge the prevailing wisdom and to look at things from a fresh perspective.
So as we move forward in our exploration of string theory and physics in general, I think it's crucial to remember that open-mindedness, creativity, and the willingness to question are just as important as the theories and equations themselves.
I couldn't agree more. The quest to understand the universe is a collective endeavor, and it requires a diversity of voices, perspectives, and approaches.
And on that note, we'll be back in a moment to delve deeper into the potential future of string theory and what it might hold for our understanding of the cosmos. Welcome back.
It's good to be back.
So, before the break, we were talking about how string theory has actually had some success
Right.
with black holes.
It has.
And you were explaining the black hole information paradox.
Yes, exactly. It's this puzzle that arises when you try to combine the predictions of classical physics and quantum mechanics.
And so how did string theory help to solve this paradox?
Well, what string theory did was provide a way for information to be preserved even as an object falls into a black hole. You see, classical physics says that once something crosses the event horizon of a black hole, it's gone forever. But quantum mechanics says that information can never be truly destroyed.
So how can those two things both be true?
Right, that's the paradox. And for a long time, physicists struggled to reconcile these two seemingly contradictory ideas.
So how did string theory provide a solution?
Well, in string theory, everything is made of these tiny vibrating strings, right?
Right.
And what string theory suggests is that even as an object falls into a black hole, the information about that object is somehow encoded in the vibrations of these strings.
Okay, so the information isn't lost, it's just transformed.
Exactly. It's like, imagine you have a book and you burn it.
Okay.
In classical physics, that information is gone. But in quantum mechanics and in string theory, the information about that book, the words, the stories, the ideas, they're still there, just in a different form. They're encoded in the smoke, the ashes, the heat that's released.
So string theory is saying that even though the object itself disappears into the black hole, the information about that object is still preserved in some way.
Precisely. And this was a huge breakthrough because it provided a way to reconcile the laws of physics with our observations of black holes.
I see. So string theory is pretty wild. It can explain things that classical physics can't,
It can, and it's opened up whole new avenues of research.
like the multiverse.
Exactly. That's one of the most mind-blowing implications of string theory. The idea that our universe might be just one of many universes out there, all coexisting in this vast, higher dimensional space.
It's like something out of science fiction.
It really is. But the idea emerges quite naturally from the mathematics of string theory. Remember that landscape problem we talked about earlier with the 10 to the power of 500 different vacuum states?
Yeah, I don't think I'll ever forget that number.
Well, some physicists believe that each of those vacuum states could represent an actual physical universe. So, in a sense, the multiverse is baked into the mathematics of string theory.
So you're saying there could be a universe where gravity works differently or where time runs backward.
It's possible. Each universe in the multiverse could have its own set of physical laws and constants, its own unique properties. Some might be similar to our own, while others could be radically different, perhaps even unimaginable to us.
It's really hard to wrap my head around that. But it's also incredibly exciting. I mean, if there are infinite universes out there, the possibilities are literally endless.
It's certainly a humbling and awe-inspiring thought,
Yeah.
and it challenges us to rethink our place in the cosmos. If our universe is just one of many, what does that say about our own significance?
Yeah, that's a big question. But for now, I think I'm just going to enjoy the ride and see where this journey of exploration takes us. And speaking of journeys, I want to touch on something Leonard Susskind said about young physicists and the future of string theory.
Oh, yes. He's been very vocal about his concerns that too much focus on string theory might be stifling creativity and preventing young physicists from exploring other avenues of research.
I mean, it makes sense. If everyone is focused on one particular path, we might miss out on other equally promising paths that could lead to new discoveries.
Exactly. And Susskind has been a strong advocate for diversity of thought in physics. He believes that young physicists should feel empowered to challenge the status quo, to question the established theories, and to explore new ideas, even if those ideas seem unconventional or go against the mainstream.
It's like we need more rebels in science, right? People who aren't afraid to think differently, to break the mold.
Yeah. I think that's a great way to put it. We need more people who are willing to question assumptions, to challenge the dogma, and to push the boundaries of knowledge in new and unexpected directions.
And that's something we can all learn from, whether we're physicists or not.
Right?
I mean, the ability to think critically, to question what we think we know, and to be open to new ideas, that's essential in all aspects of life.
Absolutely.
Yeah.
And it's what drives progress and innovation in any field.
So as we continue to explore the mysteries of the universe, let's remember to keep our minds open to all possibilities and to embrace the diversity of thought and approaches that make science so fascinating.
I completely agree. The universe is a vast and mysterious place, and we've only just begun to scratch the surface of its secrets.
And on that note, we'll be back in a moment to wrap up our deep dive into string theory and explore some final thoughts on what the future might hold for this ambitious and often controversial field of physics. And we are back?
Back again.
All right, so string theory.
String theory. It's
Ambitious, to say the least.
It is, yeah. A very ambitious theory. And we've seen how it's run into some pretty big challenges along the way.
Yeah, we've talked about the landscape problem,
Right.
the holographic principle,
Right.
the multiverse.
All these mind-boggling concepts.
So where do we go from here? Is string theory doomed?
Well, I wouldn't say it's doomed. It's more like we've hit a bit of a roadblock. We need to figure out how to navigate this new terrain.
Okay, so what are some of the ways physicists are trying to move forward?
Well, one approach is to develop new mathematical tools. Sometimes you need a new kind of telescope to see things you couldn't see before.
Oh, I like that. So we need new tools to probe deeper into the mysteries of string theory.
Exactly. We need new ways of thinking about and visualizing these complex concepts.
So it's not just about finding new answers, it's about finding new ways to ask the questions.
That's a great way to put it.
Mm.
And another promising avenue is to explore connections between string theory and other approaches to quantum gravity.
Oh, like loop quantum gravity.
Exactly. There are a lot of brilliant minds working on different approaches to unifying physics.
Hmm.
And it's possible that by combining these different perspectives, we might be able to create a more complete and consistent picture of the universe.
It's like all these different paths might eventually converge at the top of the mountain.
That's a beautiful analogy.
Yeah.
And even if we don't reach that ultimate goal of a unified theory, the journey itself is incredibly valuable. Every step we take, every challenge we overcome, every new insight we gain, it all brings us closer to understanding the fundamental nature of reality.
It's like we're all explorers, charting the unknown territories of the cosmos.
Exactly. And that sense of exploration, of discovery, is what makes physics so exciting.
It really is. And speaking of excitement, one of the things that really struck me in our conversation today was Leonard Susskind's passion for encouraging young physicists to challenge the status quo and to explore new ideas.
Oh, yes. He's been a true champion for intellectual freedom and diversity of thought in physics.
It's like he's saying, don't be afraid to be a rebel, to question authority, to think outside the box.
Exactly. And that spirit of rebellion, of challenging assumptions and pushing boundaries, is what drives scientific progress.
I think it's a message that resonates far beyond the world of physics. It's a message that's relevant to all of us, no matter what field we're in, no matter what challenges we're facing.
It's a reminder that sometimes the greatest breakthroughs come from those who dare to question the conventional wisdom and to see the world with fresh eyes.
So, as we wrap up our deep dive into string theory, I think the biggest takeaway is this. The quest to understand the universe is an ongoing journey, and we're all invited to participate.
That's beautifully said. And whether string theory turns out to be the ultimate theory of everything or not, it's been an incredible catalyst for new ideas, new discoveries, and new ways of thinking about the cosmos.
It's pushed the boundaries of our imagination and inspired countless scientists and non-scientists alike.
It truly has, and that's
Yeah.
something worth celebrating.
Absolutely. So, to all our listeners out there, keep exploring, keep questioning, keep that sense of wonder alive. The universe is a vast and mysterious place, and there's still so much left to discover. Thanks for joining us on this deep dive into the fascinating world of string theory.